Hello everyone. Welcome to Computer Science E7. This is lecture 12, Artifacts. So I hope all of you had a very happy Thanksgiving holiday and enjoyed the wonderful weather that we had. And I do want to remind you that the last assignment, assignment 4, was due today, about 4 minutes ago actually. And we will be giving you back the feedback for that assignment and the rest if you haven't as soon as possible. Also, you should have heard back already on your final project proposal. If you haven't, we may not have received it from you or something may have happened, so be sure to send us an email if you expected feedback on that and you did not. I also want to say that your banners, those will be going up throughout the week, and so we should hopefully have all of those up by next week, and we can show those off to the rest of you. So just as a quick reminder from last week, our lecture on color, we talked about a number of things dealing with color, and we introduced some of these topics by talking about how difficult of a time we have actually being very accurate with color in terms of our eyes, because our eyes and our brains more specifically can play tricks on us. And if you recall, we showed some optical illusions where we were trying to basically just show you that color perception or even luminance detection perception is difficult to get truly accurate. And we described, or we showed you this particular graph that represents basically the entire range of color that the human eye can see. So everything from the ultraviolet or near ultraviolet range all the way up to the near infrared. And if you recall, what we used, or the whole point of showing this graph was to be able to describe not only these monochromatic colors that exist on the outside, so each of these are just one specific wavelength, and more specifically just one specific color that's very, very saturated, and then all of the mix of the colors that can happen in between. So if we happen to mix two monochromatic colors, we would get a color in the middle that matches approximately what we would see on this particular graph. And the reason that this graph is useful to us is because we can use it as a way to show and to describe color spaces. So what's possible for a computer to display, or what is possible for a camera to capture, or a scanner to capture, or a printer to print out in terms of its constituent colors, and also all of the blends of colors that are therefore possible from those major colors that are possible. And so this graph and this diagram in particular is showing us the sRGB color space, because as you recall, we have three different sets of color values. So a red set, a green set, and a blue set, and each of those is described by these points on the triangle. And when we combine all of them at maximum value, we get a white that's called D65, somewhere in the middle of this particular triangle. And so if you recall, we also showed you a different color space called Adobe RGB. And how did that one differ from this color space? Yeah, so it extended the blue and the red was pretty much the same, but the green extended a lot farther into the range of greens that we can actually see. And so it's important to keep in mind that we're still describing these color sets with these 256 values, these 8 bits of values that we've been talking about throughout all this time in terms of JPEGs, but it's what each of those values represents on screen that matters, and that is what this color space is talking about. And as you recall, we were using a paint by numbers analogy, basically, where we have these numbers that are described in the file, and then the computer tries to figure out what color that number represents by using not only the color space, but also it applies the color space to that number, and then it uses the monitor profile to show you, to make that color accurate on your particular screen. And so now that we have multiple color spaces, we need a way of being able to convert between them. And so we have two of the major ways are perceptual gamut mappings and colorimetric gamut mappings. And so for us as photographers, the ones that we would typically use is perceptual. But when we are displaying colors on screen, for example, and we need it to be very, very accurate, just the range of colors that we are seeing on that particular screen, we might use colorimetric with the knowledge that any more saturated colors at either end could be clipped, and there could actually be more details there, but that's the price that we have to pay for this particular gamut mapping. Then of course we talked about profiling monitors, so calibrating them so that you will be able to get accurate color out of your monitors, and that there are different color charts out there, but this is a pretty common one called a Macbeth color checker chart. And you can use it, I mean, it's a little difficult, frankly, to look at it and just be able to discern, okay, well, I know that this red looks just the tiniest bit off. It's really hard to do that, and typically what we would do is use a hardware profiler to be able to correct the monitor to be absolutely perfect. And there do exist software tools to do that as well. They're just perhaps not as accurate, and it's also harder on your eyes because you generally have to squint to be able to get it just right. And one of the things that I neglected to mention last week that I did want to talk about was, and although I did touch on it slightly, was the fact that there are different types of LCD monitors available out on the market today. So I mentioned that there's usually ones available for desktop monitors that are higher quality than the ones in laptop monitors, but I don't think I was very specific. So just to give you a quick rundown, there's various types of monitors that exist out there today. So of course there's the CRT monitors, the big tube type ones. And that's not really what I'm referring to. The old ones could be very, very color perfect almost in a way, and you'd be able to get very nice color out of them even out of the box. But LCDs are not all made the same. There's different quality LCDs, and determining what type of panel is in your monitor is important, especially if you're going to purchase a new one. It's important in being able to get the best color. So there's a variety of ones, SIPS, SPVA, and STN. There might be some other ones available now, but basically SIPS is currently the best on the market in order to get the most color correct on your monitor. So if you're looking for a new monitor, this might be something that would interest you and might weigh your decision in one monitor towards another when looking at these different panels. So these cheaper panels, the SPVAs and the STNs, they just don't render color as accurately as these IPS panels. And typically you will find these more expensive and more color accurate panels in higher end models. So Dell has a number of models that have SIPS panels. Apple, for example, it's one of the reasons why a number of these are so much more expensive than similar ones. They just have different quality panels within them. And another thing that's important to note is, as I mentioned it before, but laptop displays are pretty significantly worse than their desktop displays. And to make this a little bit more quantitative for you, desktop displays typically can show us about 8 bits worth of color. So within their gamut that's possible, they can display the 8 bits that we know and that we are familiar with. But laptop displays, in order to make them cheaper and smaller, thinner, etc., typically might only have 6 bits worth of color information. So even if it's kind of color accurate, it's not going to be able to display all of the colors that you expect it to. And so this can be a bit of a problem for us when we need to edit our photos on our computer screen. It might be slightly off than what we expect. And so even though the software says, okay, well, you have millions and trillions of colors available, the hardware actually does a little bit of a trick called dithering, where it slightly modifies neighboring color pixels to try to simulate some colors. So as you know, what we were talking about before is that you can mix 2 colors, of course, to get a resultant color. And these hardware panels, or these panels, will try to do that same sort of trick by making neighboring pixels very, very similar, but not quite the same color. And then you might be tricked into seeing a third type of color, but it's not exactly the same thing. So that is something to keep in mind. And of course, gamma, when you're profiling your monitor, you should set your gamma to 2.2, as that seems to be now the standard across pretty much everything. And I should mention one more thing. When you do profile your monitor, you can't just call a day and quit right there. You do actually have to continue profiling your monitor at regular intervals. If it's a relatively new display, you might get away with doing it once every few months. But as the display ages, its quality also worsens, and so you might have to profile it more more frequently, or just do it, well, yeah, I mean, definitely you would have to profile it more frequently in order to determine if it's actually maintaining the color that's promised to it. And so one of the last things we talked about in regards to color is white balance, and how when we are talking about, or when we're taking a photo with a digital camera, the camera has to pick a particular Kelvin temperature that is associated with white in that particular scene. And so, as you might recall, there are a variety of whites that can exist within this color space, ranging from a sort of cool blue tones to sort of a warm red tones. And counterintuitively, the values for those are opposite what we would expect, because the blue tones, the cooler tones, have a higher Kelvin temperature than the warmer tones, the cooler ones. And the reason for that, of course, is this idea that this actually does relate to temperature. And the hotter something gets, the bluer it actually will become. So like a blue hot flame, for example, is hotter than a red flame, so on and so forth. That same sort of thing happens here. And so we used white balance as yet another reason why RAW might be a good idea for us, because it allows us to set the white balance after the fact and be able to get the most quality out of our particular photos. Any questions on all this stuff? Great. So today we're going to talk about some artifacts, and I know everybody is still sort of, hunched over from eating too much turkey, unless you're me and you didn't have any turkey at all. It's this ongoing thing. I'm determined not to have any turkey on Thanksgiving. But anyway, so I'm hoping that this will be a relatively short and relatively painless lecture, but we do have a number of things to talk about, so let's get started. So in terms of artifacts, there are a number of ways that we can get weird artifacts within our images, and so we have a word synonym for this called aberrations that can represent a number of things. So we might have, for example, optical aberrations, something that happens as a result of the optical chain. So somewhere from the lens, where the light is traveling through the lens elements, all the way through to the sensor itself. And obviously there might be other aberrations as well that can happen because of the digital conversion that can happen within the sensor, a variety of other things. We'll talk about a number of these aberrations that will happen. So as you might recall, a lens is not a very simple thing. It's a very complex object with a lot of smart people that do this all the time, trying to calculate where the light is going to bend through its path through the lens. And if you recall that one video from the optics lecture about how lenses are made, even to this day, it's not a very simple process. There is still a lot of manual labor involved in creating, especially these high-quality lenses. It's not something that can be truly automated. So sometimes we will get problems with these lenses. And even though they might be very, very good lenses, there might still be problems with them. And even super expensive lenses are not completely free of defects. So I do want to mention that, of course, we do have a front element and a back element on each of these lenses. You can get dust or grime or fingerprints on each. And as you recall from some of I think that one webpage I showed earlier in the semester where someone had actually cracked the front element in that lens, the front element is frankly not as important as the back element to keep clean. So given the choice, you really want to prioritize and try to keep the back element clean as possible, particularly because some lenses, it might be recessed into the body of the lens somewhat and might be difficult for you to get into, and that's something that you don't want to have to pour cleaning solution into and get it inside of your lens. That's just going to be a bad thing for you to do. Now, dust on the front of the lens and grime will actually cause a loss of contrast. For those of you that, like me, wear glasses and you notice that it gets really filthy after a while and you're like, oh, I can't see a thing, I need to go to the eye doctor. Then you just out of habit, you clean your glasses and you're like, wow, it's like I've just bought a new pair. It's that same sort of thing. You do need to periodically clean your lenses in order to keep the contrast relatively high. But okay, besides all of that sort of obvious stuff, there are actually problems that can happen as the light bends inside of the lens, including some geometric distortions that can happen to the path of light itself. So normally when we're looking at a point source that is, let's say it's very far away, like a star, for example. So because that light is very, very far away, as the light travels to us, it eventually becomes parallel. So what's happening here is that this is light from some very, 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 very far away object that's, essentially a point. That is what these straight lines are trying to indicate to us. So when we focus this light, we want it to also become a point on the sensor plane itself, right? So that way it is represented accurately on our sensor or on our film. Now sometimes though, there are lenses that will actually misshape the light or redirect the light incorrectly inside of the lens, and you will get this sort of strange conglomeration of photons on your sensor. And so if you can imagine what would happen if, rather than having a point source focused very cleanly like this sort of spherical aberration occurs within the lens. What do you think might happen to the image of this point source? So just imagine it's a black sky with one star that you're trying to take a photo of, and it should render just, on your image, it's just one very small point. What would it look like in this image here? So not quite like a starburst, it's just more general. It'd just be softer and just sort of like this large disk. Might look almost out of focus, or even, it has a specific look to it, but it's just going to be soft and fuzzy. It's not going to be a very sharp way of viewing this particular point source of light. Now you'll notice something else though. This happens particularly in very, very large apertures. Let's say we were to stop this lens down and get rid of some of these adjacent or some of these outwardmost lens rays. You'd be able to, if you followed some of these paths of light, you would see that these outward ones or these outside ones are the ones that are doing the most damage, so to speak, to our image. So by stopping down and using the ones that are more in the center here, we can see that we are more likely to get a sharper image. And if you don't believe this, then you can take a look at this slide and just follow the optical path and just get rid of some of the outside ones until you determine that that this is true. Now this is called spherical aberration because this lens is created as though it were from the surface of a sphere. Now, the way that optical technicians, or optical engineers rather, could fix this would be to use a lens type that's called an aspherical lens element. And sometimes you'll see this, lens manufacturers love to describe all the special sort of lens elements that are inside of their lens. And an aspherical lens element will try to correct this particular sort of thing because it will not cause such a wild variation in where this light is being focused. So, okay. So let's say now that we are taking a photo of this same point source of light, but we're not pointed straight at it. Let's say it's off to the corner of our frame. So as a result, the light is coming in at an angle. So this might be something that's off to the edge of our frame, for example. And so it's still going to be recorded on film. The light just isn't coming straight in through the lens. Now this can result in a different type of optical aberration called coma. And the light will bend in such a way that it actually will have this sort of conical shape to it. Rather than being a point source, remember it should just be one specific point on the edge of the frame. It's going to be this weird looking comet shaped, and that's actually where this name comes from. It looks sort of like a comet, and for some reason they said, oh, let's get rid of the ET and put an A, and so it's called coma. Okay, so just to show you a different image of why this might happen, let's say that we have a point source that's down here, and it's going to go through the lens and be focused onto this point up there. Now, if we take the very center of this lens, we can see that we get actually a point rendered correctly. But as we are focusing the light, so remember that the light rays are coming into all portions of this lens. So not only the center, but also these outside rings as well. So as these outside rings are focusing the light, they're focusing it in different places than where the center aspect of this lens is focusing it. So just to go back here, the rays coming in through the center of the lens go up to the correct portion, but then these outside areas are what are responsible for these really unusual rays of light. And so what this can look like in an actual photo, let's say we take a photo that looks like this. So this is, I think, just a photo some guy took of like a parking lot at night or something like that. And this photo does a good job demonstrating this problem. So we have here 3 boxes on top and 3 crops from this image, each crop representing its associated box up top. So the center box, you can see this looks correct. So these are point sources, and you can see that they look like they should, just like little bulbs of light. But in this particular lens, at the very outside, we get these weird coma shapes as a result of this lens altering the light or bending the light in an unusual way. Now, is there a way that we can correct this? Now, as you'll find out with most of the optical aberrations that exist within lenses, you can actually correct by stopping down. And so just as you might be able to tell, if we're stopping down, that means that we are getting rid of the light that is entering through these outermost areas of the lens, only using the light through the center. And so we are then able to get the most accurate rendition of that particular image. Okay, now, one of the last optical aberrations that I want to talk about is astigmatism. So those of you that, again, have glasses like me might be familiar with this term. And if you're astigmatic, then you might know that things are bad for you. They're worse than if you just have plain old 20/10 vision, or ever so slightly near or far sightedness, because objects are rendered differently than they actually appear in the real world. And more specifically, a circle, for example. Let's say if you're astigmatic, or your eyes are astigmatic, and you see a circle, what you would actually see is more of an ellipse shaped. And so it really messes up with the geometry of specific objects. It can do really weird things to the way that you view the world. Luckily, there's obviously ways that we can correct that, but lenses are not so lucky. We don't have glasses or contacts for lenses, so we have to sometimes deal with astigmatism here. So if a lens has an astigmatism problem, then what can happen is if we have a point source of light, so just a little point, just like in the previous photos, and it is bending light through all portions of the lens, sometimes this lens may not point all of those rays of light, may not be able to bend them into one specific point, but more specifically, it may bend the lateral rays, so the rays that are going in horizontally, different from the vertical rays. So this means that it'll actually modify the shape of this point as well. And so rather than you getting a very nice point source, you might get something like this area diffraction pattern, or you might get something weird like these weird, almost donut shapes that can exist. So objects, this usually happens only for objects at sort of a weird oblique angle. But if you are interested in astrophotography, for example, all of these aberrations will become a lot more obvious to you than they would in, say, perhaps real-world photography. So just going around in the streets and taking lots of photos. Just because in those cases, you really are taking a photo of point sources of light throughout the entire image. You have lots of stars throughout the image, and you can get a lot of strange aberrations there. Okay, so moving outside of the lens, we could have some other aberrations as well. And most of you will probably recognize this one. It's probably the most famous of the aberrations, called a vignette. So in a vignette, we have basically a darkening of the corners. But one of the things that you may not know is that this can happen for a lot of reasons, more than just the obvious ones. So in this case, we could have a problem of, explain to me what might be the problem in this particular image. Why did we have such a bad vignette like this? Yes?
Just a really tall building.
No, it doesn't have to do anything with the building. It has to do probably on something that we put on the lens itself. Right, so the lens shade itself, the lens hood, might be too small for this lens, and it might be causing the corners of this particular image to be too dark. And so this is an example of a mechanical vignette, something that happens as a result of a mechanical blockage of light coming into the lens. But there are other examples as well. So for example, an optical vignette can happen within the lens itself. So let's say that you have a lens that looks like this, and it's a very, very wide aperture lens. But if you look through the lens, not straight on, through the side, for example, you'll see that you don't actually see a perfect circle through the end of that lens. And this is a perfect example of an optical vignette. You are actually being blocked because of the design of the lens. This portion of the image circle, this entire portion right here, is being blocked by the barrel of the lens. And this may not seem like that big of a deal, but if you take a photo with a lens that looks like this, you will actually see the result is quite a big deal. So if you take a photo that has with this lens and use a very low f number, very wide aperture, you would get in the center exactly what you expect. This very nice bokeh that has very circular, out of focus areas. But then as you move towards the outside of the frame, keep in mind that the outside of the frame are objects that are going to be off to the side and shining their light through the lens like this, then you might get these sort of cat's eyes view of the bokeh. So you can see here that rather than being perfectly circular, it's almost elliptical. It's this cat's eye shaped instead. So there is even one more way that we can have a vignette as well. And unfortunately, this one is a little bit more complicated, but this deals with the way that the light flows, or the way that the light is focused onto the sensor itself. So if you remember oh man, I'm blanking now. This is happening with surprising frequency, isn't it? So the inverse square law, that's what I was talking. So when we were talking about flashes, we also were talking about the inverse square law, where we have light fall off due to the distance of that light. So that's not exactly what's going on here, but you can use it as sort of an analog. If we have a lens, for example, a very wide angle lens that has to get somewhat close to the sensor in order to focus its light. Now it's the light that it sends onto the sensor is going to be very sharp. It's going to be very oblique angle. So this light here has farther to travel than the light that goes right to the center of the image. So we might have an optical vignette because this light, because it has farther to go, might fall off. We might have this light fall off problem. Now it's more complicated than that. It's not actually this reason. What may be more accurate would be that the micro lenses on this sensor here are just not designed to capture light coming in at an oblique angle very well. Another reason might be just similar to the way that when the sun goes down at the end of the day, because it's at a harsher angle, it's not bearing straight down, there's not as much heat being passed through to the surface of the Earth. That's another thing here. So all of this light that's being sent here is just not as concentrated, so to speak, as the light that is being sent right to the middle of the image. So we could have this, what's called natural vignette, that can occur, especially in wide angle lenses, as a result of just these optical properties that can occur. Now, there are ways that optical engineers can correct for this. Obviously, the longer or the more parallel that the light comes into the center, or to the sensor, rather, the better this problem will be. So we can eliminate this natural vignette by making this light fall very, very perpendicular onto the sensor itself. And that's indeed what happens in a lot of the modern lenses. So luckily now, natural vignette, I would argue, doesn't happen a lot in the higher end wide angle lenses as much as it may have in the past, just because these engineers have figured out a way to get around this particular problem, and this could be correctable nowadays. Okay, any questions so far? Lots of good stuff so far. Yeah.
So it seems like in order to help correct vignetting and a lot of the other aberrations,
Mm-hmm.
it seems like more lenses are put in there to accommodate that. But doesn't that reduce the power of light that's entering the lens in the first place? Because you're putting more and more.
So by putting more and more elements of the light, we would be decreasing the amount of light that's actually entering to the end. So, so I would say that with, I mean, it depends on how the lens is designed. I think with properly designed lenses, I don't think adding more elements will necessarily make it much darker, especially since a lot of the loss of light occurs from reflections of the light. So if these lenses or these glass elements are not properly coated and the light is reflected off of it, then that's where we lose a lot of the light from them. But if they are properly coated, as we see in optical glass and especially very high-end filters, then more of the light is passed through and only the frequencies that we don't care about, like the infrared or the ultraviolet frequencies, are then blocked out and reflected off. And that will allow more of the visible light to pass through with less reduction in contrast due to flare or ghosting. So as light bounces around between the elements inside, that's where we see a lot of the lens flares and ghostings that can occur, especially when we're pointed at a very strong light source, like the sun, for example. Lens flares are very common in that case. But as our coatings get better, then I think that problem starts to disappear. So we're battling that problem, what could be a problem in that case, with newer technology, with other advances in that particular arena, if that makes sense. So, but yes, I mean, it is possible with every glass element you add, there is an additional risk of it, but there's ways to mitigate it as well, especially when these optical engineers are actually dealing with the design of the lens in its entirety. They can probably be able to do it. Okay, now one of the things you'll notice about these vignettes is that some of them are actually possible to correct by stopping down, while others are not. So for example, a mechanical vignette, this one, I mean, if you have a hood that's too small, or if your hand is blocking it, or if you have a filter in front that's too small for the image circle and you're actually blocking some light in, then you may not actually do any better by stopping down this particular, by stopping down the lens. However, if you do have an optical vignette, as is the case in this one where we have the cat's eyes, then obviously stopping down is going to help a lot, because this smaller aperture will actually allow the light that's being passed through to come in even at these strange angles, these off-center angles, and be able to go in all the way without bother to the sensor itself. Natural vignette, this is a physical property of light, so if your lens naturally vignettes, then there's nothing you can do. No amount of stopping down is going to be able to help you. So one of the things, if you remember, that digital camera manufacturers are saying that they are really improving the way that their light gathering capabilities is improving the micro lenses on their sensors. And this, I think, does a good job of showing us how improving the micro lenses might be able to give us better light gathering performance, especially at the outer edges and the corners of a frame when we're dealing with very wide angle lenses. So the better that we can deal with these oblique light patterns, then the better that we will be able to get our photo to be. Okay, now there's other optical aberrations as well that can happen because of your lens. So distortions. Now these are particularly bad in consumer cameras, but as you start spending more and more dollar signs on lenses, then you generally see these particular types of distortions go away. Now, if you look at a lot of digital camera reviews, you'll actually hear some mention usually of barrel distortion or pincushion distortion. That is what this is referring to. So if we have some object that should be rendered as a perfect square on the image, we take a photo of this square with the lens that either has a barrel distortion or a pincushion distortion, then we will see this object rendered like this or like this, respectively. So a barrel, imagine that you have a big barrel and you basically have printed out your image and you wrap it around this barrel and you look at it straight on. That's what this looks like. It's sort of bulging out like a barrel would bulge out. And a cushion, the pin cushion, well, this is perhaps a little bit weaker, but imagine that you have a pin cushion and you have an image on it and you're pushing on that pin cushion, and then that is the result that you would see from this. And so it's important to realize that these are separate distortions than the sort of distortion you would get from a wide angle perspective. So if you are using a very wide angle and you get close to your object, you don't necessarily have to get either barrel or pincushion distortion. It's important to note that these are distinct things. So frequently, classes of lenses like wide angle lenses and telephoto lenses are susceptible and are prone to specific types of aberrations. I think specifically wide angles are prone to pincushion distortion, and telephoto are prone to barrel distortions. But you should be able to, in an ideal world, there are ways that we would be able to remove these distortions from our images. And just to show you a couple of examples, I have here 2 images that should be perfectly straight or perfectly square. And I would use this stick as a way of showing you how straight it is, but obviously this is not going to help very much because it's not straight itself. But here on the left, this is an example of which distortion? Yep, barrel. So it bulges on the side, as you can see a little bit. And this one on the right, this building, pincushion. Yep, because it's a bit thinning. So it looks a bit thinner than it should normally. It's not actually perfectly straight up and down. And it's most noticeable, I think, on the edge of this particular building. And usually when you see a review for a digital, especially a consumer camera which has a fixed lens, or if you see a review for an SLR lens by itself, you will generally hear some mention of either barrel or pincushion distortion. And unless you're dealing with, I don't think it's really that big of a concern unless you're dealing with some consumer camera or some consumer lens. Then that is when you should probably pay attention to what they're talking about, because I think nowadays, as especially the higher quality lenses have gotten rid of a lot of the distortions that are found there. But it's not to say that this problem is eliminated altogether, because you can definitely purchase cameras that have these particular distortions. So it's important to pay attention to, but I think really only if you're dealing with some of the lower end of some of these things. Okay, hope I haven't lost any of you yet, because we have some more good stuff coming up. One of them is this topic that I've been talking about and referring to for a long time, but never actually got around to explaining it to you. That is this concept of refraction. So now we were talking about some of the things that can happen as a result of the way that the lens is engineered. So some of the problems that can happen because we have misshaped glass elements, or we're a bit lazy, or we want to produce a lens that's a little bit inexpensive, so we wanted to cut some corners somewhere. Now we are going to deal with some aberrations that can occur because of the actual physical properties of light. And one of them is this concept of refraction. So many of you might know this through things such as a prism or through water, for example. When you're looking at an object that's under a pool, it's not exactly where you think it is. And this, as you know, comes another way we can say this is if you have a pencil in a big glass of water and it looks broken, that's because of refraction. And what happens is that as light enters this interface from one medium to another, so for example from air to glass, so in this case this is a glass prism, then it changes speed. And as it changes speed, its direction also bends slightly. But even more importantly, is that each wavelength of light bends a different amount depending on its frequency, because these wavelengths of light have different energies, and so they bend at different quantities. So as you can see, as we refract this light through a prism, and this is why when you put sunlight through a prism, you see this rainbow of colors, is that the light is bent and each of the frequencies is separated, and you see a rainbow of colors on the table or on the sheet of paper next to the prism. And unfortunately, this is something that we have to battle with constantly. Well, we being optical engineers, so really they have to battle with constantly when they're designing lenses, is being able to figure out how they can bend or alter the path of light without getting each of these colors to split. And what can happen if that happens is we get something that looks like this. So let's say we have a lens. So this is in the more traditional lens shape. Remember that this is the same sort of thing. We have a point source of light that's nearly infinity distance away, and we're trying to take a picture of it. And it should render as a perfect circle or a perfect dot on our sensor. But as the light enters the lens and as it refracts through the lens, then the colors split. And so we can see if this is our film plane right here, we might have optimized this lens for, say, the green wavelength, which is a pretty good way of doing things, especially in older lenses. Then we can get the green wavelength perfectly in focus, but the blue and the red wavelengths are slightly out of focus. So even though the green might be perfect dot, we would get this sort of weird color halo around each of these dots. And the same thing would happen if the light was slightly off center. We would get this weird sort of aberration that, almost a rainbow just off center if we were looking at an object that is not directly in the middle of this image. And just to give you an example of what this might look like, there's two images here. The top one is optically decent. The bottom one has this chromatic, what's called a chromatic aberration, that results because of this refraction that can occur in the lens. So pay particularly close attention to the sides. Where you see here, there's this sort of hue of blue off to the side, and on the other side, there's this hue of red that exists on each particular edge of this building. And that's because the red and the blue wavelengths are out of focus in different areas, and the green is focused just fine. So we get not only this sort of blur, but also we get these weird color fringes that can exist on each particular size. Now, or on each particular side rather. Now imagine what would happen if we took this photo in black and white. How would this look? Yeah, just fuzzy, just really blurry, really fuzzy. And it would be difficult if we had just black and white to differentiate this from this being out of focus. It would just be difficult to be able to tell. And so really, this has been more of a problem lately, especially as well, not particularly lately. I mean, I know color film's been around for a long time, but I'm just saying that it's now especially a problem, especially now that we are doing what's called pixel peeping. So those of us with digital cameras, I know you love to take photos, bring it home and show it on your screen at 100% and look at each individual pixel and say, nope, not sharp enough. Well, this is not something that was really done back in the film days. I mean, you would have magnified it and viewed it in a larger size, but there's no concept of pixels really in film. And so we didn't have the same sort of problem. So arguably now, I think manufacturers being pushed harder than ever to design glass elements and lenses as a whole that are more optically perfect because of these very fine levels of pixels that we have in each of these images. Now, a related chromatic aberration that can occur is something that's very, very familiar to those of us with consumer cameras, or rather just compact digital cameras. That is this purple fringing. So if you notice around the horse's mane, the horse's ear, and up, all the way up there, there's this sort of purple tinge to the light. And this happens especially with backlit objects or very high contrast areas, such as this case where the hair is somewhat dark, the background is somewhat light, and you're getting this high contrast change. And you see this noticeable amount of purple fringing. Now, this is distinct from the chromatic aberration due to refraction that we saw before. Usually, purple fringing deals with, frankly, the micro lenses that exist in front of a camera's sensor. So if you have a relatively inexpensive consumer digital camera, its micro lenses may not be made to the same specifications as that of a much more expensive digital SLR. And so those micro lenses usually, just like we have in this particular example, where we have a lens and we can optimize its use for perhaps one wavelength, usually those micro lenses will be designed to focus the green wavelengths very well, not these other colors. And so sometimes this is the result, is that because this blue and this red are slightly out of focus, we get this very strange chromatic aberration. So this is a problem, and this can even happen even if you don't have an inexpensive camera, even if you have the price of a small car, digital camera, flagship from Canon or Nikon, you could still get purple fringing from lenses. So I'm not saying that lenses are not at fault for this. It's just that usually, typically, it deals with the sensor itself. Sometimes these inexpensive lenses will also, well, I mean, not even inexpensive, but just any lens can be prone to purple fringing or fringing in general in very high contrast regions of a scene, particularly at the outside ranges of that particular lens. Now, there are some fixes for this. Usually, camera manufacturers and lens manufacturers will use a glass element called fluorite, which has a very low level of optical dispersion. And the whole point of this fluorite is that it does not change the speed of the wavelengths as much as just a regular glass element would. And so all of these wavelengths of light get focused into the same point. Now, the downside is that fluorite is extremely expensive, and typically even the most expensive lenses will only have 1, maybe 2 fluorite elements within them, but they will be they'll be very well corrected for these optical aberrations as a result. Okay, so there are ways that we can correct these optical aberrations, and some of them are unfortunately expensive, like buying better equipment. Sometimes you don't have that option though, and so usually what you should try to do is stop down the lens. So don't use it wide open all the time, but stop it down, and you'll be able to get rid of a lot of the optical aberrations that exist for that lens. Now, lenses are designed, as you know, with a specific image circle in mind. So as light enters the lens, it's focused onto a circle that is cropped basically by the sensor, because the sensor is square. It's not actually a circle. And the very outside edges of this circle will have the most problems, as you've seen, because it's a result of where this light is being focused. It's just more difficult for the outside regions, particularly the corners of a lens. So usually the hardest thing for a lens to do is to be used wide open, which means the lowest F number possible for that lens, and to look at the corners of that particular shot. That is going to be the most stressful for the lens, and sort of one of the best tests for how well corrected that lens is. Now, as soon as you stop down that lens and use something more along the lines of maybe f8 or f11 even, then you will correct for a lot of these issues, because you will be using the center portions of the lens, which will be just inherently better and more corrected than the outside portions of that lens. Now, for a digital SLR lens, generally the range that's ideal is about f8 to about f11. You generally don't want to go much higher than that because of a different concept called diffraction that we're going to talk about next. And you generally don't want to go lower than that. Well, if you can get away with it, you don't want to go lower than that, because then you will get these optical aberrations as a result of using a very low F number. So generally with a digital SLR, you should aim for, especially if you need it to be absolutely perfect, you should aim for something around f8 or f11. Now, compact digital cameras, I would say the same, but unfortunately diffraction comes into play much sooner there. So you exchange these optical problems for a softness, and don't worry, I'll explain this more in just a little bit. You exchange one thing for another much more quickly in a compact digital camera. So generally you might need to get away with something like f5.6, maybe f8, but I suspect that on most compact cameras you're going to be diffraction limited in those cases. So stop down. If you have your camera on a tripod, you're taking a landscape shot, for example, just set it to f8. Just do us all a favor, because if you use this lens wide open, unless you really need to on a landscape shot, you might be disappointed in how relatively soft your image looks versus that same lens on at f8 or so. And even the sharpest lenses in the world do benefit quite a bit, or well, I mean, it varies, but they do benefit by stopping down at least a couple of stops. Okay, let's see. I think diffraction is an interesting topic, but I think we should wait 5 minutes before we talk about that. So let's take a 5-minute break. When we come back, we will talk all about diffraction. All right, hello everyone, welcome back. So we did run a little bit late because everyone was curious about my Thanksgiving story, and that's why you should come to lectures, because you get to hear all of my rants off camera that I also happen to mention. And so, but with that said, we do need to talk about some of the interesting stuff as well that's not related to my holiday plans. And that deals specifically with diffraction. And so diffraction is the thing that I've been talking about for a long time, and this goes all the way back to lecture 1 when I took the photo with the pinhole, the pinhole lens, and I posed the question, why is this not sharp? Why is it fuzzy if it if everything in the image is supposed to be in focus. And the reason is due to this optical phenomenon called diffraction. So those of you that have a good memory and remember your high school physics might remember a couple of experiments that deal with something that looks like this. So usually you might see something like, us younger folks have had the luxury of using like lasers, but I know that even in earlier high school programs they would use like large water tanks to show off this particular thing. And so all of these things are related because they all deal with basically waves. And so as you remember, light can operate not only, or has characteristics of not only a particle because of the photons, but also waves. And so it's this waves aspect that we're focusing in on right now. And what happens very generally is that we have a set of waves that are coming in and it hits some obstruction that has a narrow slit in it. And so as you can imagine, this is analogous of a lens that has small aperture within it. And so as the waves pass through this slit, they actually basically wrap around the edge and vary their distances to the other side. But because they vary in distances ever so slightly, we get these weird patterns where sometimes the waves get out of phase and they basically cancel each other out. And there's some portions which become in phase and can not multiply, but they are as strong as they were before the slit itself. So we see that after this wave has entered through this slit, we get through the center the same wave, but then as we progress outside of this particular portion, we get alternating aspects. So it gets a little bit, there's not as much of a wave right here, it's softer. Then there's another wave right here, and then there's no wave right there. And just to put this into motion, we can see this in a ripple tank. So this is a very similar thing. You will see something that looks almost exactly the same as that still image that I showed you. It's just going to be not quite as high in resolution, so it's harder to see each of these aspects of in phase and out of phase for a particular wave. Now let's see. Okay, so here we can see that there's some equipment that they use to show us this particular thing, including some light equipment and mirrors and projection screens and all sorts of stuff. Then of course they also have to have a ripple tank as well, where they have a slit right here and they have some device that actually generates waves in this water. Remember that this is applicable because waves in the water are just like because light operates as a wave, we can use the waves on the surface of the water as an analogy. So we can see that we have this slit here, and the waves propagate out. They sort of they fan out from the center of that slit. So the same thing happens in light. So as the light comes in through this slit, it doesn't just come straight down to the sensor, it also sort of bends and fans out a little bit as well. So the smaller the aperture slit here, the more this is going to become a problem. And in fact, just go back here, what this actually looks like with a point source of light that's poking through a very small slit in say this piece of paper or this wall, is that we have the point in the middle and then this sort of these concentric circles, these donuts that go outward from that circle in the center. Now, I would be very surprised if your digital sensor was actually had enough megapixels in it to actually see this exact pattern. But imagine what would happen if you were expecting this one circle to be right in one pixel, right here. And then, of course, you have neighboring pixels. What would this circle look like if you had pixels that were about as large as this center circle right there? So you would see that one center pixel is bright red. But what about these neighboring ones? You'd see they would be just slightly red, right? You wouldn't see this detail because we're talking about pixel level here, but you would see that there is some noticeable amount of red. And so if you actually make the slit smaller, the size of this concentric circle, or this donut shape, will increase. You'll cover more pixels. So what happens then? So you have this red that's supposed to be covering one pixel is now covering multiple pixels. Let's say these 9 that are surrounding it, and it just becomes fuzzy. becomes out of focus. And that's, well, not out of focus, that's incorrect, but it looks out of focus, it looks fuzzy. And that's exactly what can happen when we are dealing with this. So let's say that we take a photo at an aperture of f5.6, which is still relatively large of an f number. Then we stop down to a very small f45. I don't recommend this at all for digital, but you get to see exactly what happens. We destroy a lot of the detail because of this diffraction problem. It just becomes soft. It wraps around this narrow slit that happens to be inside of our lens, and it causes this weird pattern to emerge that you don't see. You don't see that specific wave pattern, but the result is this fuzziness that can happen in your image. Now, because, as you know, pixels vary in size from one sensor to another, so some sensors have very, very small pixels, whereas other sensors have large pixels. Different digital cameras will actually be impacted by diffraction at different f numbers. Okay, because remember that diffraction is going to happen basically anywhere that light passes through an aperture. But the larger the pixels that we have, the less likely we are to capture the problem, the surrounding concentric circles around that disk. So if we have smaller pixels, like we do in, say, digital cameras, then we're more, or rather compact digital cameras, more specifically, then you're going to start to see diffraction much sooner. And this is one reason that adding more megapixels into already burdened compact digital cameras, and even digital SLRs these days, which are now growing ever so high in their megapixel counts, we're seeing this diffraction problem sooner and sooner and sooner. So just to give you an idea, so we've talked about, or I think we've referenced this particular website at least once before, and I want to do it again because they have a very, very good tool online that not only talks about the same sort of thing, but it also has this neat little diagram here that we can use to try to determine how diffraction will impact us. So it has here a list of f numbers, or rather apertures, and some cameras and associated pixel sizes. So if we actually take a look at some of the pixel sizes, and keep in mind that these are old cameras, so these pixel sizes are larger than they are now. This is an old Canon 1D, which is probably, I don't know, 8 years old now. It's pretty old at this point. You can see that the pixel, these dotted lines here, is actually pretty large. So I'll just keep going down, 1DS, okay, it's smaller, all the way down to a Canon PowerShot, which is a small compact digital camera. You can see how small the pixels are on this particular sensor. Now we can see that if I modify, let's go back to the 1D here, I can modify the aperture. So the larger the aperture, the less likely I am to have this diffraction problem. Because the smaller the slit, the more this is going to be a problem. So if I go from f2 on a particular lens all the way up to f32 on a Canon 1D, you can see how that what used to be a point has now become not out of focus but blurry due to diffraction. And so this one point now covers these 9 pixels, and it's going to look soft and blurry within the image itself. Now I'm just going to go down to a pretty reasonable f8 in this case on a Canon 1D. Then I'm just going to start going down the list of cameras to make the pixels smaller so that you can see, even though I'm dealing with the same size of the aperture, and this is somewhat misleading because normally when we shrink the camera sensor size, what do we also have to do to the lens? For the same field of view, we have to shrink the focal length of the lens, which means because the aperture, the f number is a ratio, we're also shrinking the size of the aperture as well, so the size of the hole when we're talking about this. So f8 in a Canon PowerShot G6 is probably already going to be much smaller than the aperture of a much larger camera that has a much larger lens. Okay? If that doesn't make sense, then review some of the earlier lectures. But I think here they're assuming that the aperture is going to be for the same lens, so that it will generate the same pixels. So assume that we're using the same lens for each of these pixels. Okay, all of that technical detail said, we start making the pixels smaller and smaller. and smaller, and we can see that now, whereas before we had no problem due to diffraction at f8, now a compact digital camera has this same problem that we had at much higher f number for a larger sensor, or rather, and more specifically, a larger sensor that also happens to have larger pixels. So as we increase the megapixel count in these, we're going to have these problems. As we decrease the size of the sensors, we're going to have this problem. As we decrease the size of the lens itself, and therefore make the size of the aperture smaller, we're going to have this problem. So we're working against all of these problems, and modern digital cameras, digital SLRs, unfortunately from Nikon, because Nikon is now, or no, not Nikon, Canon seems to be getting into this really kind of stupid idea of increasing their megapixels ever so frequently in their digital SLRs, whereas Nikon, thank God for them, are keeping their megapixels somewhat low, which means that we're not running into this problem because the pixels are the same size from camera to camera. But on Canon cameras, if you've upgraded to one of the newer like 50Ds or the 70s, the pixel size is so small that you're getting diffraction limited at about f8 or f11, whereas before you could have gotten away with f16 with the very same lens. And in fact, I've started using a 7D, and that's exactly what's happened, is that I've noticed that with these lenses I can't go above f8, and it's frustrating and it's annoying because I sometimes want a greater depth of field. And so you have to exchange sharpness in terms of focus for softness due to diffraction. And so there's no, unfortunately, really good way of fixing this except having, monstrously sized sensors. But then, of course, we have to pay for that in actual cash dollars rather than in any sort of optical way. Okay, anyway, so diffraction is bad for us because it increases the softness of an image without us wanting to do it. So it's counterintuitive because we thought, and we've been told up until all of this time that, increase the f number and you'll get more in focus. You'll get a sharper image than what you had before. And that's true up to a point, but then after you reach this diffraction limit, you will start just getting softer and softer and softer images, and it will just become increasingly frustrated. So you can use this website. I believe it has a calculator at the bottom where you can actually figure out the f number that you can use without being diffraction limited in your particular camera. And you might be surprised at how relatively low of an f number that actually is for your particular camera. So that's something to keep in mind, and it's something that means that if you want to really get the optimal quality out of your lens and out of your camera, if you have a digital SLR, then I recommend sticking to about f8 to f11. Any smaller of an aperture, you'll start getting diffraction limited pretty much for most digital cameras out there today. And any larger of an aperture, you will start getting optical aberrations from your lens. So if you want the best, f8 to f11 is probably the way to go unless you have a very exceptional lens. Now on compact digital cameras, you will have to experiment, but you may frankly be screwed no matter what you do, because you'll either have optical problems because of low f numbers, or you're going to be diffraction limited due to high f numbers. And so you would have to frankly determine what will be the best, but generally, again, f5.6 to f8, even on those, would be a good starting point for you to figure out what is the best thing for you to do. Okay, so we talked about a lot of optical artifacts. So we've talked about artifacts involving the lens, artifacts involving properties of light itself, but there's even more artifacts that can exist just because of the nature of digital photography, the nature of the sensor, what we have to do in order to process the images. And we've talked about some of these. So can you name some of these artifacts that we've discussed already? Here's a hint. Let's say you increase the saturation a lot of an image. A lot. It's something like posterization. Oh, good. Okay. So did somebody say that, or did I? Okay, maybe not. So I made you all look smarter, I guess, on camera. Okay, anyways. So posterization is one. We talked about that, where it causes this gradient, what used to be a smooth gradient have visible steps in it. Another one is, of course, the noise. So the noise that we've seen, that's, it partially has to do with the optical properties as well, but it has a lot to do with the sensor itself. Then blooming, I think I mentioned very briefly. That deals with when you overexpose a particular region. If you really badly overexpose it, the overexposure sort of spills to neighboring pixels, and it makes a bad problem even worse. But there's other things that can happen as well. So if you recall, we have a filter on the very top of the lens. So above the micro lenses, we have this filter called an anti-alias filter. And I mentioned it briefly, but here's a different example of what this thing does. So aliasing is making something more jagged. So if you have something that's aliased, then it's going to have what should be a circle. When you zoom in a little bit, you're going to see these jagged lines because of each of the individual pixels will be visible within it. Now, if you anti-alias something, you're making it a bit softer, and you're making the interface from that solid colored region to a different colored region a bit smoother. So from this yellow to this blue, you can see that now we have a few more colors to deal with, sort of yellow blues, but it's a softer interface. It looks a little bit better. And so this gets rid of the so-called jaggies phenomenon. So typically we have, you see something like this, and people love to call this jaggies, and so that's what we're able to get rid of by anti-aliasing a particular aspect. And so if we remember that we are using an anti-alias filter on the front of a digital sensor, and we have to do this because each pixel doesn't actually capture one color. So, it doesn't capture all colors. It has to rely on the neighboring pixels to be able to capture or to recombine it later and figure out what that original color was. That can cause weird artifacts when we have very highly alternating patterns. So if it was a lot of lines, as we saw back here in the diffraction one, so if it's a lot of lines and it just so happens that these are different colors and it's alternating from white to black to white to black. Take a picture of this, and each of these colors falls on one pixel on your camera because you're sufficiently far away. Then it has to guess, and it might get it wrong. It might try to make all of this sort of a gray color like this area just because it's recombining this color incorrectly. And so we have this anti-alias filter to try to make it smoother and eliminate this problem, this high frequency pattern, or this high frequency pattern, same thing, it's twice. So this high frequency problem, eliminate it altogether. Now, there do exist problems that can happen from aliasing. So if we have an image of a building, and this has a very high frequency pattern, as you can see, it goes from the red brick to the white mortar and back and forth very, very quickly. Let's say we shrink this image just ever so slightly, and we don't use any anti-aliasing. Okay, so we just shrink the image ever so slightly. The computer has to decide which of these pixels to keep and which ones to throw away. And sometimes, if you get it just right, you'll get a pattern that looks like this, where sometimes it has to pick more of the red brick pixels, sometimes it has to pick more of the white mortar pixels, and that's just because there's no finer level of detail. It just can't, it has to throw some detail away and keep other amounts of detail. And so as a result, we get this sort of weird ripple effect that can happen on this brick wall. And this, the result of this is called Moira. And so you might see this, you'll see this especially on compact digital cameras, which might have to have a weak anti-alias filter in order to get some detail out of the particular scene. But so the ones that you might recognize and what might be more familiar are these examples where we have, if you remember, this was some folded over jeans. And so if you know the thread on the jeans alternates from dark blue to a white very, very quickly. And the sensor is incorrectly guessing what the color should be. And more specifically, the camera's computer, the CPU inside, is incorrectly determining what the colors were that made up the original scene. And so we have to use an anti-alias filter to smooth out those details and essentially just get rid of them so that we can just get some higher quality amount of detail than what this provides. And so sometimes you will see some effects like this, Moira and maze patterns. So you still see some Moira. You see the Moira in the colors. You see how it's a patterned orange to blue to orange to blue. That's Moira. Then also you see this maze pattern, which looks just like this maze of pixels. So those are two distinct things that can happen as well. And so the internal processing of the camera can cause this Moira to occur and for these maze patterns to appear. And so again, using this anti-alias filter on the front of the sensor helps us eliminate this problem. Now, to try to combat this anti-alias filter, because as you know, using it will make it a bit softer, we can try after the fact to sharpen the image again to try to make it look a bit sharper, a bit crisper, like it might have when you originally took the photo. But the problem with this is that you can definitely overdo the sharpening and you will make it look just plain wrong, just really strange and very unusual. We can get this effect called sharpening halos as a result. So let's say that we have this very heavily anti-aliased circle, as you can see here. Now, this might be nice if this is what you wanted to do, but if you want it to be a sharp, crisp circle, you then need to alias it again. You need to sharpen it somehow. So you might use one of Photoshop's sharpening filters, and actually the one that, and what photographers generally recommend is something called an unsharp mask. And we'll probably talk about that in the, I think we referenced it briefly before, and we'll talk about it again in the upcoming software tools lecture. But generally using this, you can then retrieve some of the sharpness around objects. And basically you can think of it as it finding the edges of something and trying to increase the local contrast. So it's trying to increase the contrast of edges. So it might find an edge interface here, and it might make the inside a little bit darker and the outside a little bit whiter, and that will give the effect of making it look sharper. The problem, though, is that if you overdo it, you will get black on the inside and white on the outside, and it will give this halo effect, which will look fake. It will look bad, and you can see the result of decent sharpening here. So zoomed in, it's not the sharpest thing in the world, but it's still pretty good, as you can see compared to our first image here. Or you can overdo it and just get these weird white halos that surround your circle. And this is generally a bad thing. And cameras, out of the box, will generally apply some amount of sharpening to try to combat this anti-alias filter that they have to use. So generally, when you buy a camera and it's set to JPEG mode by default, you take a couple photos, you put it on your computer, and it looks reasonably sharp. The reason for that is that this sharpening in camera is combating with this anti-alias filter. But sometimes manufacturers go a little too far with the default sharpening, and it can be over-sharpened. Maybe not to this degree. This is certainly an extreme, but just enough that it doesn't look quite right. So you might need to turn down the sharpening in your camera, or again use RAW in order to be able to apply your own sharpening to the file as you process it. So again, yet another plug for RAW to be able to process something as best as possible. Now, of course, when we're talking about digital artifacts, we also have to talk about lossy compression as well. So artifacts that can result due to compression. And so JPEG is particularly prone to this particular problem. If you save a JPEG file in a very high quality, it's always lossy, but it's not going to lose that much data. You will still retain a lot of the detail that exists within it. But, and we've referenced this before when we were talking about file formats, as you compress something very heavily, you will get very strange compression artifacts because it has to throw some data away. So here you can actually see pretty well, I think, the blocking that occurs within JPEG. So you can see that there's these sort of large blocks that just are not visible in this higher quality. And so decreasing the quality in JPEG, which I'm sure most of you know already not to do, but this is really just an extreme example of the compression artifacts that can happen. So using a very low quality, while it will save you some space, will be bad for the quality of your photos. And certainly you should save I'm sure I've mentioned this, but just to mention it again, if you take photos in RAW, or rather, I'm sorry, if you take photos in JPEG, I recommend as soon as you download them, you make 2 copies. One copy that you're just going to save in its original pristine condition, and another copy that you should feel free to modify however you wish. And if you're very careful about just always using save as, for example, then maybe you don't need to keep 2 copies. But I don't recommend overwriting your original image, because once you've overwritten it with JPEG, you've lost a little bit of data. Nothing like this, but you've lost a little bit of data. You're never going to retrieve it again. So you really should be careful with compression artifacts when resaving JPEG files. So if you do use in-camera JPEG rather than in-camera RAW, I recommend you go into your camera's menu and you set the JPEG setting to the highest quality possible. It will use a little bit more space on your CF card or on your SD card than just the smaller JPEG quality, but you will get the highest quality possible out of it. And usually, the way that camera manufacturers show this to you is usually something like almost literally like this. It's sort of like a quarter circle, and you either see something that's, sort of very jagged or something that's very soft, and you generally want something that looks the higher quality, the smoother version of the quarter circle, and that will be the best way to go. And that's it. So next week we'll talk even more software tools, and we'll talk a little bit about masking, some more tools that are very useful to us as photographers. And we only have 2 lectures left. So thank you all for coming, and we will see you next week.